Hi, I'm Alex, and I'll be presenting our paper High Performance Texture Streaming and Rendering of Large Textured 3D Cities. I will start with the motivation and challenges for rendering large 3D cities and present our new contributions for it. Then review some related works and show how we improved on them. Next, I will cover the components of our texture streaming system, show its results, and evaluate its streaming performance and rendering quality. Finally, I will end with the conclusion and future work. Many cities now provide a 3D digital twin for geographical information system purposes. These 3D cities often contain millions of textures produced from an automatic process. For example, the Berlin City dataset has 5.7 million textures, 41 gigabytes in size, and the Helsinki dataset has 25,000 large texture atlases, 3.5 gigabytes in size, both in BC1 compressed format. One major challenge to render textured cities is the limited amount of GPU memory. Although computer systems can page overflowing data from GPU memory into system memory, it is very rudimentary and will severely impact rendering performance. One simple way to fit these textures in memory is to reduce their resolutions globally. However, this will result in fuzzy, low-quality rendering. Existing methods perform visibility detection to load visible textures for rendering. They also change texture resolutions during runtime based on some level of detail metric. The disadvantages of these methods are the expensive CPU and GPU operations. Rendering artifacts such as texture pop-ins are also very common. What we want to achieve is a high-performing texture streaming system that is GPU-centric and requires only a single rendering pass. We also want to have high-quality rendering with minimal frame rate stuttering and texture pop-ins. The contribution of our research is to enhance the texture streaming pipeline. We propose to amortize hardware virtual texturing costs using adaptive texture streaming algorithms to minimize frame rate stuttering. We also propose a runtime texture caching method that is semi-compact and suitable for non-uniform dimension textures. It is fast, multi-threaded, and requires only a single rendering pass. We also restore original mesh colors for low-resolution mipmaps to minimize distracting texture pop-ins. Finally, we provide a mesh discretization scheme to generate texture atlases. This is an optional step, but it improves texture streaming performance and reduces texture caching memory. Related work in GIS. Geographical visualization systems stream and render large city models on the web. They often adapt texture resolution based on camera views, where the camera is looking, screen space metric, how many pixels does a building cover, and the client's rendering time and available memory. Some limitations of such systems are the need to pre-generate texture atlases, numerous GPU state changes when switching between textures which impacts rendering performance. These systems also do not use virtual texturing with in-shader address translation. To address these limitations, we propose a runtime texture caching strategy that supports texture atlases and individual textures of different dimensions. We also use virtual texturing to eliminate expensive texture state changes where mesh textures are updated. Related work in virtual texturing. Virtual texturing maps scene textures, including mipmap, in the virtual texture space. This process is called megatexturing, where the virtual texture is discretized into regions, also called pages. Physical memory is allocated for those pages needed for rendering. During rendering, per fragment page address translation is performed to sample the actual physical texture. Some limitations are: there is no hardware support for texture filtering because page boundaries are not contiguous. Per fragment address translation is also inefficient because of multiple texture memory fetches. To address these limitations, we choose to use hardware virtual texturing to easily support anisotropic texture filtering and improve texture address performance. In hardware virtual texturing, page address translation and texture filtering are managed by the GPU. In Vulkan, the hardware virtual texture is interfaced using the sparse partially resident image. This sparse image is like an image object with multiple mipmaps and layers. Physical memory blocks can be allocated and bound for regions required for rendering. Some of its limitations are: finding memory blocks during runtime is very slow and is a system-level limitation. We noticed there is a quadratically increasing cost when binding memory blocks, which leads to stuttering frame rates. It is also not designed to cache textures with non-uniform dimensions because it uses one set of texture coordinates to address all mipmap levels. For these limitations, we propose adaptive texture streaming algorithms based on GPU load to minimize frame stuttering. We also propose a texture caching scheme that allocates memory during runtime to directly support textures of non-uniform dimensions. For our texture streaming goals, we need to cache city textures that have various rectangular dimensions. Our texture streaming system also needs to be fast to cache and retrieve textures using parallel algorithms. It also needs to minimize frame rate stuttering during rendering and minimize distracting texture pop-in effects. Additionally, we want to optimize and reuse texture caching space, and we want our system to be robust enough to perform across different city datasets and computer systems. Our strategy to minimize frame rate stuttering is to stream an ideal size batch of textures per streaming cycle. To find this ideal batch size, we estimate from the GPU load. This GPU load is used to adaptively adjust the streaming batch size and mipmap levels. To minimize texture pop-ins, we store original mesh colors, then blend them with the sampled low-resolution mipmaps. To achieve robust performance, we introduce parameters to balance rendering latency with texture streaming performance. We use the Vulkan Graphics API to support our parallel texture streaming and rendering pipeline. We also take advantage of Vulkan's sparse queues and transfer queues for asynchronous executions. Here is an overview of our texture streaming pipeline. Under preprocessing, we generate texture atlases. Under CPU, we have the main rendering process and the texture streaming process both running concurrently. Under GPU, we have the fragment shader to gather visible mesh metadata and the compute shader to compact this array before sending it to the CPU. We will go through each of these processes in more detail. The first pre-process is generating texture atlases. This step packs mesh textures in atlases for improved texture streaming performance. We first discretize meshes into uniform regions, then within each region, we further discretize meshes based on similar orientations. We then pack textures of the same height in each subregion into an atlas. Finally, we fill empty spaces in each atlas using the next in order textures of the same height. The CityColormap stores the entire scene's original mesh colors. We blend original colors without sampling errors, with the erroneous low-resolution mipmaps in the sparse image based on loaded mipmap levels. This will significantly reduce texture pop-in effects. Below, you can see the generated CityColormap for the Berlin scene. The first step in the texture streaming pipeline is to generate visible mesh metadata in the fragment shader. We calculate the visible mesh metadata, specifically a mipmap level and a weight value, in the fragment shader with early z-test. The mipmap level defines the mesh mipmap to be streamed. It accounts for anisotropic filtering in both streaming and rendering. The weight value defines mesh perceptual importance, which equates to its texture streaming priority. By default, we add 1 to the weight value per fragment for priority based on mesh screen space size. We also add 0 to sigma depending on the camera distance, because many small meshes near the camera can be quite visible even though they have a small screen space size. Lastly, We add 0 to row depending on mipmap level. This is to maintain a similar and even resolution for streamed mipmaps. The next process in the pipeline is to compact mesh metadata in the compute shader. Because the mesh metadata array gathered in the fragment shader is sparse, transferring the entire array to RAM per frame is slow. We want to compact this array in the compute shader using a simple atomic counter. We set the parameter tau equals 300 to cut off meshes with small weight values from texture streaming. Note that the parameter tau is proportionally related to the weight values defined previously. This parameter balances the total number of textures streamed with the overall texture streaming performance. The texture streaming process invokes the texture streaming task group with 4 main subprocesses. The first subprocess is loading texture image data. We load mipmaps in parallel, addressed by the mipmap level metadata. We do this by maintaining 3 texture object states: initial to mipmap to final. The initial state indicates that texture is loaded for the first time. We reserve a location in the sparse image and allocate and bind underlying memory and move on to the mipmap state. The mipmap state indicates there is a lower mipmap level to be transferred. We also allocate and bind underlying memory for each of the loaded mipmaps. We move on to the final state if the base mipmap is loaded or if the texture is invalidated. Additionally, we introduce an adaptive mipmap bias to influence the loaded mipmap level based on GPU load. We show the rendering result of the Berlin city dataset on the left. On the right, texture mipmap level is visualized as grayscale. As the camera moves, textures are loaded based on mipmap level. The next subprocess is caching textures in a sparse image. We pack mesh textures with the same base dimension in the same sparse image layer, filling from left to right, top to bottom in parallel. Layers are filled in a ring buffer order, reusing the oldest layer if all layers are filled. Having less sparse image layers equates to a faster texture streaming performance, and having more sparse image layers will result in less cache thrashing. We also can pack rectangular textures with the same maximum dimension in the same layer. This can reduce the maximum number of layers used, but will not fill those layers compactly, potentially causing more cache thrashing. Here we show level 4 textures mipmaps being loaded and cached inside the sparse image as the camera looks at different areas of the scene. Just like loading mipmaps, this process is performed in parallel using atomic counters. The next subprocess is the texture streaming exit condition. We designed a scheme to stop a texture streaming cycle based on a batch time and a batch size. This is to prevent overloading the GPU with too many memory binding and texture transfer commands. The batch time terminates the batch process when the defined time is elapsed. We choose 60 milliseconds as it is our target rendering latency. Having a shorter batch time will produce a more responsive display of new textures, and having a longer batch time will result in lower multi-threading overheads. The batch size terminates the batch process when the size is reached. Having a smaller batch size means less frame stuttering during rendering, and having a larger batch size produces a higher rate of textures streamed. This batch size is adaptively adjusted based on estimated GPU load. The final sub-process in the texture streaming task group is GPU load estimation. To support our texture streaming design, we propose a function to iteratively estimate current GPU load, L, based on n previous GPU load measurements, Li. The GPU load L influences the adaptive batch size and adaptive mipmap bias algorithms. How it works is if the current memory bind time T is high, GPU load L will immediately assume the high T value. If the memory bind time T is low, GPU load L will fall off towards the low T value, based on the fall-off rate R, shown in the equation on the right. This equation shows that the GPU load L will always choose the maximum between the weighted average of previous memory bind times and the current memory bind time. We also propose the adaptive batch size function to suppress high fluctuations in rendering latency during texture streaming. The output of the function, batch size S, will decrease exponentially if the GPU load LF is high. The parameters target bind time TB and exponent alpha control the magnitude of batch size reduction and increment. In the equations below, we compute the batch size S from a defined batch size scale, S in lowercase, modified by the reduction factor F. We make sure to clamp the batch size S to a minimal value to ensure continuous GPU load estimations, even when the streaming system is performing very slowly. Additionally, we propose the adaptive mipmap bias function to suppress high fluctuations in rendering latency. It also maintains an even mipmap resolution for loaded textures during streaming. Mipmap bias B will increase smoothly to the maximum bias Bmax if GPU load LB is high. Otherwise, no mipmap bias is introduced. In the equation below, we use a smoothing function to scale the maximum mipmap bias Bmax based on estimated GPU load LB. I will now present the results of our texture streaming pipeline, evaluated using the Berlin City dataset on a high-end computer system. We measured an average frame latency of 5.66 milliseconds and a maximum frame latency of 15.37 milliseconds, with an average transfer rate of 13.7 thousand mipmaps per second and a maximum transfer rate of 28.9 thousand mipmaps per second. This video shows the benchmark fly-through of the Berlin scene. On the left, we have a baseline method with no adaptive texture streaming and mipmap color blending. On the right, we show our adaptive algorithms with color blending at work. Severe frame rate stuttering and texture pop-ins are visible in the baseline method. The first chart on the top shows the frame latency of the Berlin rendering. Although a large spread of rendering latency from 2 to 15 milliseconds is measured, the perceived frame rate stuttering is minimal as the maximum frame latency is below the target latency of 16 milliseconds. The second chart shows the decreasing mipmap transfer rate as the number of memory block allocation increases, shown in the third chart. These charts indicate that our system adaptively reduces mipmap transfer rate when memory block bind time increases, successfully maintaining a stable rendering latency throughout the simulation. Here we evaluate our adaptive texture streaming algorithms. We found that there is a wider range of mipmap levels streamed when the average adaptive batch size is lowered. This may cause uneven mipmap resolutions during streaming, which can be remedied by increasing the average adaptive mipmap bias. The adaptive mipmap bias algorithm by itself cannot regulate frame stuttering. This is because there is an innate memory binding performance cost even when streaming small mipmaps. Hence, we need both adaptive algorithms for texture streaming. We want to test how robust our system is, so we apply the Berlin optimized system parameters to Helsinki dataset, which has a higher geometry count and uses large texture atlases. Still, our texture streaming system managed to suppress frame rate stuttering and maintained an even distribution of mipmap resolutions. However, the texture streaming rate is non-optimal as the target rendering latency parameter does not reflect the higher average rendering latency for the Helsinki dataset. For this parameter, it is scene and computer system specific. To solve this, we can simply set the target bind time value slightly higher than the average rendering latency. To evaluate texture pop-ins, we compare our color blending method to direct mipmap sampling. There is a significant change of average color intensity between frame 0 and frame 1. We measured a maximum mean square error of 26 using our method versus 124 using direct mipmap sampling. Hence, by gradually introducing higher frequency texture details, we managed to significantly reduce texture pop-in effects. Here is a close-up view of the rendering result using our color blending method compared to direct mipmap sampling. In frame 0, both methods sample from the original mesh colors. And in frame 1, we blend in very little high-frequency details from the maximum mipmap level, while direct mipmap sampling shows pervasive sampling errors in the low-resolution mipmaps. And in frame 2, we blend in some more high-frequency details from the second highest mipmap level. This video demonstrates the texture pop-in artifacts as the camera moves around the scene. In the baseline method, texture pop-ins are clearly visible in meshes coming into view at the right edge. In our method, higher resolution mipmaps are blended in based on mipmap level, minimizing the texture pop-in effect. We also compare our texture streaming system with Unity's because game engines are increasingly adopted for GIS purposes. These game engines provide better user experience and optimized rendering performance. They also have support for virtual and augmented reality development. We tested the same Helsinki dataset and measured an average rendering latency of 20 milliseconds in Unity versus 19 milliseconds using our method. In Unity, we noticed mipmaps are refined based on camera distance and memory pool. Initially, low-resolution mipmaps are displayed with erroneous mipmap colors, which causes distinct texture pop-ins when higher resolution mipmaps are loaded. This is the rendering result of Unity. As the camera moves closer to the mesh, higher resolution textures are loaded and immediately displayed. Here is our method. Higher resolution textures are gradually applied as the camera moves closer. And here is the result when switching to a new view in Unity and panning the camera to the side. And this is the same test for our method, showing significantly reduced texture pop-in effects. One limitation of our system is cache thrashing. When all the sparse image layers are filled up, currently visible textures may be unloaded and reloaded into the cache again. We solve this by increasing the number of sparse image layers, but this increases the memory pool and impacts texture streaming performance. We also can solve it by lowering the mesh weight cutoff threshold in the compute shader. To conclude, we have provided a high-performance texture streaming system for rendering 3D cities with large numbers of textures. Our system is multi-threaded, GPU-driven, and requires only one rendering pass. We created two adaptive algorithms with GPU load estimation to maintain a smooth rendering latency and an even mipmap resolution throughout the rendering. We also blended original colors from the CityColormap with low-resolution mipmaps to minimize texture pop-ins. Under testing, our system is robust to support different city datasets and computer systems. As for future work, we like to explore virtual texturing in remote and web rendering. We want to investigate the possibility of shader-based virtual texturing with remote address encoding and decoding. Lastly, we'd like to thank the National Research Foundation in Singapore for funding our research, and the respective Berlin and Helsinki agencies for openly providing their 3D city dataset. Thank you for watching.